A couple of years ago, around early 2021, after watching Ben Ear's video series on building an 8-bit computer from scratch on breadboards, I decided to pursue a similar endeavor in constructing my own 8-bit computer from scratch. There was one problem though. I didn't want to just build his SAP1, which consists of limited features. Well, I eventually did, but I originally wanted to design and build a custom computer that had some tangible usability. And after researching some other computer builds online, I wanted to venture even deeper and construct a computer of much more capability than I initially had in mind. Anyways, after a couple of years since those thoughts and my last update video, hundreds of hours wiring, hundreds of hours researching online, and even more hundreds just debugging, I present to you the current state of that computer, which I've named the hippo8. This video will be a rough overview of the current state of the computer, which, as you can see with all of these debugging wires, is not yet finished. And I want to note before I go into detail about the current design and specifics. This past summer of 2025, I got my first real chance at hammer away at the project. As other years, I had school stuff to worry about, and the occasional free weekends and breaks didn't speed up development that much. I don't really know when will be the next chance I get to work on this computer again, so that's one other reason why I decided to make this video. One last important thing before jumping into details. About 2 years ago, I decided to pivot from an original design, I know, what a shame, and base my computer design off an existing one that I found online, namely the build by DerULF 1, which I will link his channel and links in the description, which you should definitely check out. I did this frankly due to a lack of knowledge and a lack of time. So note that my build is heavily based on his computer build, and you should definitely check out his channel, which I watched religiously and based my hardware off of. As you already know, my system is an 8-bit system, meaning the data width is 8 bits. The address width for indexing to memory, however, is 16 bits. So for a brief overview of the computer layout, we have the 8-bit data bus here on the right, and all of its corresponding 8-bit constituents. And on the left side, we have a 16-bit address bus. All these wires here on the left, and it's all of its necessary registers. Down here on the bottom left is all of the hardware for decoding instructions and controlling the computer, which you'll see in a bit. Starting up here on the top left is the system clock for syncing the entire system, which is very similar to Ben Ear's design, with the 355 timers in astable, monostable, and bistable mode. We can toggle between monostable and astable mode with this button right here, and we can step through the clock manually with this giant push button. Moving down are the three 16-bit registers that the computer uses to handle memory addresses. Up here in the green is a program counter, which keeps track of the computer's current location in memory. It has control lines that allows it to count up and load values from the address bus as to allow for jumping. Right below the program counter is the stack pointer. My stack in memory counts down, so the stack is currently near the top, and is similar to the program counter except for that one function that can also count down. Finally, in red here is the transfer register, or new address register, which essentially is the middleman between the data bus here on the right and the address bus, which runs down these ribbon wires down here. Specifically, it serves the purpose of moving values between the two buses, so we are able to load addresses, for example, for memory, loading the low byte and then the high byte onto the transfer register in order to be accessed by the 16-bit registers. Up next, or should I say down next, at the very bottom of the address bus, is the system memory, which is split up into ROM and RAM. Addresses are 16-bit wide, so the computer is able to address up to 2 to the 16 or 65,536 bytes of memory. The ROM is 8K bytes and consists of the upper 8K of the address width. And specifically, my memory RAM is memory mapped so that the computer accesses ROM when indexing to memory by the stack pointer, or the program counter, and indexes into RAM when indexed by the stack pointer. As such, as you can already figure out, the upper 8K of RAM is reserved for the stack. Similar to Banner's build, there's also a toggle switch for switching between system access and manual access, so I can modify the data manually. Moving on to the data side, the address registers are able to output their data onto the data bus, but we also need registers to manipulate data. Here in red, you can see the 4 general purpose registers this computer supports: the A, B, C, and D registers, which are all identical in hardware, with control lines to write and enable over the bus line. The hippo8 can directly manipulate data using these registers, which are hard-coded into the instruction set. Right below the general purpose registers with these massive wires is the accumulator, or what I like to call the E register, which is tied directly to the arithmetic logic unit, or ALU, right below. My ALU supports a variety of functions, such as the arithmetic, addition, and subtraction, as well as bitwise logical operations such as AND, OR, XOR, bitwise left shift, and right shift. The outputs of the ALU, as an accumulator does, is latched by the E register up here, so that one input is from the data bus and the other is from the E register. Additionally, the ALU sees a flag register right below here in these green LEDs, and what I like to call the F register. The F register consists of the overflow, negative, 0, and carry flags, and sees control lines that allow it to choose whether or not to latch the output of ALU flags. The flag register also sees a control line to set or clear the carry in for ALU functions, which enables multi-byte arithmetic. Regarding the process of building and debugging the ALU, the ALU has been the most error-prone portion of the CPU, and has been a constant source of troubles throughout my build. So that's why there's so many jumper wires here currently that I've been using to test fixes, but I think most of the issues have been resolved by now. Onto the computer's outputs and the LCD. Highlighted here are the 7-segment display and the LCD that I've implemented. Here's my 7-segment display. I have the controller up here and the display down here, honestly due to poor board real estate management. But the computer can simply write to the output register, and an EEPROM, similar to Banner's build, decodes the signal into its corresponding 7-segment format. I can also cycle through the unsigned and signed versions of the data, as well as a binary and hexadecimal form. The LCD is a little bit more complicated. Up here is a port controller from DerULF's design that helps control for I/O such as the LCD, the PS2, and the future SPI bus. It helps the LCD read and write from the data bus, which is connected through these wires over here. Moving on to arguably the most complicated part of my computer's hardware is the instruction decoder and control logic. Here with the small red LEDs is the instruction register, which the computer uses as a starting point to begin decoding instructions. And to the left is the instruction decoder, which, for a brief overview, just because it's pretty complex, simply decodes the current instructions and the combined flag states of the computer by indexing into these two ROMs, and outputs a meaningful starting address for the control logic down here. So you can see brown wires coming in. These are from the CPU flags, and gray wires over here from the instruction register. That all gets decoded and fed into the control logic. And the control logic down here, which basically takes in the starting addresses and steps through the microcode of each given instruction and outputs the necessary 48 control signals down here in yellow for the computer into what I call the control word. The control word basically consists of all those control lines which tell the computer which parts to turn on and off during an instruction. When I started building this project, I tried color coding the wiring, and I think it worked out pretty well for the individual modules until I started running out of different colored wires. But anyways, if you take a look, especially on the 8-bit, along the 8-bit bus, all the yellow wires are control lines from the control word. So once you take a broader view, everything seems pretty connected, with everything being connected to the control word. Last but not least, tucked next to the control word right here is the PS2 controller, which is not finished but is based off of DerULF's design. I thought I'd just add it here since I already constructed it. Okay, now that I've gone over the hardware of the computer, I'm just going to quickly demonstrate an example program I've got here on the ROM chip loaded up. A simple Hello World program, which just consists of some basic LCD initialization and sending byte data over the bus to LCD. But currently I'm still loading programs manually through the ROM chip. Hopefully someday I'll get the SPI bus working so I can load programs through the SD card, which will make things much easier. Currently the computer is clocked at around 3000 hertz. Reset and start. Oh, there we go. And data flowing through the buses. And down here, you can see hello world. Not too sure why the exclamation mark became a question mark, but did say the computer's still pretty buggy. Anyways, that was about 4 years of my life's work. There are still some big problems with the computer, and programs are still extremely buggy. Notably, the way the control word is being outputted down here, apparently the EEPROMs I've been using have a momentary undefined state after they're addressed, which has been the bane of my existence for the past 2 weeks. But that is a problem for future me. Software-wise, I haven't even gone over my troubles writing software for this computer. I wrote a custom assembler to assemble the computer's custom instruction sets, as until recently, I've never even written an assembly before, but I've been learning. I still need to figure out how to write more complicated programs for the computer, which will definitely be troubling in the future. Hardware-wise, I still of course need to get the PS2 controller working, as well as a SPI bus for the SD card reader working, as described by DerULF in his build, which, as you know, I'm a big fan of. Other than that, the hardware is mostly complete. Enough for this video. Overall, this project has been a huge learning experience for me so far. Please feel free to leave any questions or comments about the hippo8 you have down in the comments below, and I will gladly answer them in a timely manner. Goodbye.